These are the class activities for lesson 1 for Math 205. We want to complete the empty parts of the table. So I'm dealing with descriptions of sets. If I want to talk about the set of all integers that are greater than 15, the roster method means list them all out. So integers greater than 15 would start with 16, 17, 18, etc. And then set builder notation, I would say the set of all values A such that A is an element of the integers and A is greater than 15. Okay, my next set, 1, 2, 3, 4, keep all the counting numbers up until 99. So I would, in words, I would say counting numbers from 1 to 99. And in set builder notation, I would say it's the set of all numbers x such that x is between 1 and 99, so 1 is less than or equal to x is less than or equal to 99, and x is an element of the integers. Set of all x's such that x is prime and x is less than 10. So I want all the prime numbers less than 10. The roster method, just list them. So 1 is not prime or composite. It's a special thing. So it is not included in this set. 2 is prime. 3 is prime. 5 is prime. 7 is prime. 8, 9, and 10 are not. So I don't include those. 2, 3, 5, and 7. That's my entire set. A set of all x's such that x is prime and x is smaller than 10. So in words, I would say all prime numbers smaller than 10. Number 2, write R3 using set builder notation using vertical vector notation. So R3, that is set of all 3 entry vectors x, y, z, such that x, y, and z are elements of the real numbers. Give an example of 3 elements in the set of vectors that look like A, B, A, such that A and B are elements of R. So 3 vectors that live in there would be 1, 3, 1, because the first and last entry have to both be the same. They're both A, and then the middle entry can be something different. Another one might be pi, 0, pi. And another one might be 4, 4, 4, because the middle entry does not have to be different. It just isn't always the same. So the first and the third entry are always the same. The middle entry could be something else or it could be something different. So if I wanted to describe this in words, I would say the set of all 3 entry vectors where the first and third entries are equal. Number 4, give an example of 3 elements in at squared plus bt plus b such that a and b are integers. Okay, so I'll just have to pick integers a and b and plug them into this format, at squared plus bt plus b. So I could have 3t squared minus 2t minus 2. Another one would be negative 4t squared plus t plus 1. And one more, 18t squared plus 5t plus 5. So to describe this in words, I would say it's the set of quadratic functions where the coefficient on t and the constant term are equal. Okay, this is part of your homework, so I'm going to skip over that for now. Writing proofs, this is also part of your homework, but I think I'm going to do one of these with you. This theorem 2 was done in the demo, so we'll do one more here. Prove that the sum of an odd integer and an even integer is odd. So we're going to say let n be an odd integer and let m be an even integer. And we want to show that n plus m is odd. Okay, so if n is odd, then n is 2 times an integer plus 1. For some j in z, some integer j. If m is even, then m is 2k, 2 times an integer, so now let's see what happens if I add n and m together. N plus m is, well, n is 2j plus 1, and m is 2k. So when I add them together, I get 2j plus 2k plus 1. And then if I look at just the first two terms, I can factor out a 2. So I have 2 times j plus k plus 1. So this is 2 times an integer plus 1. That's the definition of an odd number. So I can conclude n plus m is odd.